trying to give you a little bit of an overview of, what robustness is about, in particular, what the problem is. And kind of, we in particular advertise this, emerging goal of adversarially robust generalization, in which kind of you don't just want to find model parameters theta that lead to a classifier that has, expected loss of this classifier is small. You are now kind of adding this max term that kind of you want to say, oh, if I sample, an example from my distribution, and I look at its worst case perturbation, like the worst case loss I can get via perturbation, then I want this to be, to be small in expectation. That's kind of this goal of adversarial robust generalization, which is exactly tuned to kind of prevent emergence of adversarial examples. Okay, and kind of, I already said that, in some ways, both empirically and kind of essentially, like also, well, in some ways in theory, we are succeeding in achieving this goal, so that's good. But kind of course, as much as it's good to have tools that work, the emerging thing is, and that's what we'll focus on today, is kind of like, but why? Like, in particular, if we look at these two regimes of like the standard learning, where we just take worry about this average case, expected performance, and we look at this adversarially robust learning, where we care about robustness and generalizing in this adversarially robust way, like how do these worlds differ from a fundamental point of view? Like what kind of phenomena emerge in one and maybe do not emerge in other? And also, like, so this is the one question in particular, as we will see, and that's something that happens in practice, like learning robust classifiers is hard, and it will be good to get some intuition why. And the other thing is that, like, okay, I spent the last lecture telling you all about all the kind of ways in which machine learning classifiers fail in terms of reliability and brittleness. And you might ask, okay, we know why kind of we did not design them to be robust, but like, why do they fail so badly, as we have seen in the first lecture? So we would like to dig a little bit into trying to understand the underpinnings of this widespread brittleness. Okay, so that's the plan for today, and let's start with talking a little bit about some of the theoretical, like foundational reasons why learning robust classifiers might be much harder than learning standard classifiers. Okay, and kind of the best, the first kind of question I want to ask is, do robust models overfit? Okay, so what do I mean by this? Okay, so if we are in the standard learning, standard learning world, well, the way things work is that you just I'm just sorry about that, the joys of giving talks from home. So anyway, so yeah, so when we look at the standard at the standard learning, then kind of we have this, when we train the model, we train it on our training data, and kind of if you look here, we have a plot of how our accuracy on the training data grows as we start training our models. So kind of, we see how this curve goes. And of course, like it actually goes all the way to 100%. And like notice that the largest line is at 105%. So essentially we are completely fitting the data, by the time where when we kind of finish training. And that's good. It's nice that we can completely explain, in quotes, the training data. But of course, the danger is that, okay, so we don't really care about the performance on the specific training data we have. We care about the performance on the test data, the withheld test data that we will be kind of tested on. And kind of, there's this big worry that, it's not hard to give correct answers to the questions The question is like, how do you generalize to the questions that you don't see yet? And kind of the worry is that you might be overfitting, that you might kind of figuring out a, kind of a way to answer the questions the training example, fitting the training examples you have in a way that is not generalizable to other examples.
Excuse me.
However, yeah,
I have a question about this graph over here. Is this the accuracy is measured with respect to the training data or the?
Yes. So for now it's with respect to training data. So this is like standard training, so-called training accuracy. So it's kind of just how well do we fit, the training? That's again. So there's nothing surprising about getting 100% here. What is surprising is that if we now look at the performance on the actual test data, the withheld data, then actually see that our performance is no longer 100%, but it's not much smaller. And this is one of the successes of, in particular, the deep learning kind of toolkit, that indeed these networks tend to generalize really, really well. So even though kind of, we train them, and you might say there are many reasons to believe that they will overfit, they just don't. Essentially, they really are very good at this drop from this 100% of fitting the training set to whatever we actually do on the withheld data set tends to be very, very small. And that's kind of one of the magic, or one of the key reasons for the magic of deep learning, why we kind of, we use it so much. Okay, so this is how situation looks in the context of standard models. But now the question is how do things look like when we talk about robust generalization? Okay, so again, as we talk about, you can use robust training to start trying to essentially classify your training set robustly. And it takes a longer time and it's a little bit more painful, but in the end, you also can, with enough work, you can make your neural network fit robustly your training set. So you can get the robust accuracy to actually be, close to 100% on your training data. But now the question is, what does happen on the withheld data? How good your robust accuracy is on withheld data. And when you look at that, then unfortunately you will see that there's actually quite a large drop in performance. So even though you seem to be able eventually to fit the training data well in a robust manner, your robust accuracy on the withheld data is actually not so great. So there is a huge a nearly 50% drop in accuracy when you do that. And again, of course, this is not the first time we encountered this kind of phenomena. In the standard learning, we also dealt with this. There were some different regularization techniques that were kind of developed to try to mitigate this effect. But for robust accuracy, we tried stuff and other people tried, and we couldn't really find anything that was super effective. And this kind of started to make us wonder, what's going on? Why? Maybe there are some fundamental reasons why this kind of robust generalization seems to be so much harder and so much worse than the standard generalization. And indeed, we found at least one reason why this happened. And essentially the reason, the realization here is that to generalize in a robust manner, it's not just a matter of being ingenious in training and training hard and so on and so on. It's actually that the amount of data that you need to generalize in a robust manner might be actually significantly larger than what you need for standard generalization. Okay, specifically the theorem that we proved, and again, this is more of a proof of concept theorem, it's not super deep math. In fact, in the exercises, you will essentially prove it, is that the sample complexity of robust generalization can be significantly larger than that of standard generalization. And just to be more precise, so what essentially one can show is that there exists a d-dimensional distribution, so a data distribution that lives in the dimensions, where essentially it has this interesting property that I just need one sample from this distribution, and I can find a classifier based on just this one sample that essentially allows me to correctly classify all the other samples from the distribution, with very high probability. So I can get, with one sample, one training example, I can build a classifier that is very, very good on this data distribution in the standard sense. However, unless I have seen square root of d samples from the distribution, then it's informationally theoretically impossible for us to find a classifier that essentially achieves better than essentially trivial accuracy in a robust sense. So essentially, if I just now insist on being able to classify correctly the the samples from the distribution, if the adversary can perturb them slightly, then essentially I cannot do much better than random. Okay, so essentially this is the best I can hope for. And of course you have to be precise what small perturbation means, and this is kind of roughly what are the parameters we look at. They are kind of reasonable, and again in the exercises you will look into it a bit more. Okay, and in particular, what you will analyze there will be just two essentially like heavily overlapping Gaussians will end up kind of being this kind of, like when one Gaussian corresponds to one class, the other Gaussian corresponds to the other class, and they are quite overlapping, and that seems to be already a simple example of such distribution. But then again, this is the statement that we want to make, and this is a statement that's actually true. And just to give you a bit more intuition, I want to tell you, like walk you through the proof of this theorem, or at least like hand-wavy proof of this theorem for linear classifiers. So essentially, we just kind of how would you prove this theorem if this was just about classifiers? Like the only classifiers you can use are linear classifiers. Okay, so kind of the distribution, this hard distribution would look as following. So first of all, you would just choose a vector, a theta star, which is just a the dimensional plus minus one vector. Like think of this as a kind of a key or random seed for the distribution, because remember, like if the distribution was fixed, then I don't need any samples to kind of to find a classifier that generalizes well on it. So I need there needs to be some secret, that kind of I need to try to learn during training, and essentially the value of theta, is this secret. And now essentially the way we define distribution D is that if I want to kind of, well, I will either choose a positive example, so label being +1, or negative example, label being -1. And the way I do it is like once I choose which example I want to get is, well, I will now sample kind of my feature vector X, where essentially each vector, like each feature is chosen independently random. And kind of the process that via which you create is just you start with X being either theta, if the theta star, if the example is if the example is positive, or minus theta if the example is negative. So that's kind of the first step. And then what you do is essentially you do a noisy flipping. So essentially what you do is that essentially you take each bit of this X and you flip it with probability 1/2 minus tau. So it's kind of, it's not completely flipping it at random, because then you would be erasing any information. It's just kind of a tiny bit biased flipping with some kind of bias tau over here. Okay, so that's the construction of the distribution. So it's a very simple construction where you kind of, it's everything is ±1 vectors here, and again, like you have this theta star is kind of the prototype of a class, or minus theta star is the prototype of the negative class. But then kind of you only see this X after this noisy, through this noisy channel that kind of with probability 1/2 minus minus tau, it flips the the bit independently, each bit independently random. That's only how you see the X's. Okay, so this is the distribution. And now observe that if this is my distribution and I just get one single sample from the distribution, so X0 and Y0, then I can choose the classifier to be linear and just to be essentially a classifier where, this classifier W is just my example times the label. Okay, and when you do that, then notice that now if I sample some new example from my distribution, then essentially the value of this classifier on the value of this classifier essentially on on this point X, essentially if you do the calculations, will be roughly like essentially in expectation it will be like 4 times D times tau square, and then due to this due to this biased rounding, essentially it will be it will have a it will have a like a variance, or like essentially standard deviation of square root of D. Okay.
Sorry.
Yeah.
I have I have some trouble with the notation. Belongs with the subscript R means it's random, or
yeah. So sorry. So like whenever the belongs with the subscript R means I just choose uniformly at random from the set.
And so what is X0 Y0? So what
X0 Y0 is any like it's just one sample, like a specific sample from the distribution. So I just take one sample from the distribution. That's my training set, and based on that I construct my classifier. So
Y is a single bit plus minus.
Yes.
1.
Yes.
And X is a
vector.
And so
yes.
X0 and Y0, they have the same type. Yeah, X0 is a vector and Y0 is a single bit.
Yes.
Okay.
So essentially, this is either plus vector X0 or minus vector X0.
Mm-hmm.
So this is still a vector. So essentially, like so this is this is roughly what you get. And essentially, like the point is that if you set now tau to be roughly like, some constant over d on the 1/4, then essentially you make sure that this bias always survives this kind of noise of rounding. So as long as you make sure your flipping of the bits is not, too severe, kind of this bias always survives. And essentially, like, and this way you kind of get, the classifier to be essentially almost always correct. Kind of, it's, like it's very unlikely because, like, yes, of course, this noise, like essentially you model this as a Gaussian noise, like you need to use some tail inequalities, and it can be significantly larger than this, but it's very unlikely that it will be significantly larger by this. And essentially, that most of the time your classifier answers correctly. So this is kind of the easy part, that like with one classifier, you can generalize for the distribution, in the standard way very easily. However, now kind of the problem comes in is like, imagine I use the same, I use the same classifier, but I would like now to think about, whether it is robust or not. So imagine that what I do is that, like, before I essentially, like, essentially whenever I have a sample, what I do is I just add to it this perturbation delta star. Okay, and the interesting thing is that this perturbation delta star does not really depend on X. It just depends on the label, like, essentially, like whether I want to make this point look like a negative point or a positive point. And all I just have to do is I just have to look at my classifier. And essentially, like, I just have to, in some ways, look at the, like this classifier like works bit by bit. So essentially, I always round, like essentially, I always kind of flip this bit or like push this bit the wrong way. Okay, and essentially, if I then kind of gather together, well, the first two terms over here will be exactly as before. That's kind of the basic bias plus the noise. But then I have this adversarial noise that the adversary can always make sure goes in one direction and kind of orchestrate, all these biases go in one direction. And I have this bias of, epsilon times the L1 norm of W, which essentially is just epsilon over D kind of negative bias that the adversary can use to essentially like mislead my classifier. And then as long as you set epsilon to be also like 1 over d to 1/4, and again, this is like a tiny noise because each entry is either +1 or -1. So this is like a subconstant noise I add to each of the coordinates, but I do it in an orchestrated manner. It's not random; it's orchestrated manner. You essentially can always make this classifier being correct. So this essentially shows how this specific most natural classifier fails, and then if you think about it, it actually works for any classifier, linear classifier that you can. You can show that it doesn't work. So interestingly, if you were able to use arbitrary classifiers, then essentially like generalizing even robustly from this distribution is very easy, even with one sample. All you just have to do is just essentially do the first, before you apply your classifier, you just round the coordinates to the, either +1 or -1. And the moment you do that, essentially you are erasing all of the noise. So, everything is back, the analysis goes the same as in the standard learning. So, the distribution works for linear classifiers. It doesn't work for arbitrary classifiers. And that's, in the exercises you will work an example, these Gaussians, which works even, even if you try to do something very creative and nonlinear over there. Okay, so this is a little bit of theory, and then, but how does it look in practice? It's good to prove theorems, but like, do they actually manifest themselves in practice? And the answer is yes. So essentially, if you look at kind of essentially like, so these are like different training sets, different data sets, and essentially what you look is that you have just kind of this curves, like the blue one corresponds to just standard training, that like the adversarial noise is 0. So we see that like as a function of the size of the training set, like what is the test accuracy we get, and we see that very quickly it kind of achieves already like its kind of maximum value, while for like the robust generalization there is a lag. It takes a while until you actually get to the value you are looking for, and kind of this affects this kind of lagging effect you can see on many other data sets. Indeed, like essentially if you like for a fixed training set size, it's not only that your robust accuracy is worse than the standard accuracy, but it's also that kind of the moment where you tend to achieve close to maximum robust accuracy tends to be much further into the as a function of the training set than for the standard. Okay, so this phenomenon seems to be real.
So in the
okay?
in the first and third panel, it seems like the red line will never approach the blue line. Is this correct?
Exactly? Yeah, exactly. So essentially, we didn't have enough data to get kind of to the moment where this curve starts to flatten. So yeah, so that's exactly the point. So in some ways, this makes sense in some ways. It's because these data sets were created for some reason, and kind of in some way, you can say they were a little bit calibrated to standard accuracy. So like no one and it's hard to get more data. So that's exactly the point, that like kind of it seems that we just don't have enough data. Especially like on the second panel, actually, like you see that you have only towards the end of the size of the data set, you see this sharp pickup in kind of inaccuracy. And actually, I should have said, like, people developed a way to use unlabeled data points kind of to augment the robust training, and it helps a lot. Like it actually starts to like essentially you can push this curve further, and it only then starts to flatten out. So essentially, so there is a way of showing that this seems to be at least one of the phenomena in play. Okay, great. So this was about like that this robust generalization needs more data. But here's another question that kind of we were wondering about. Is just this question was, okay, clearly training a robust classifier is difficult, but like once you go through this pain, you would expect that your classifier this robust classifier is clearly the best of the best you could hope for. Like kind of it should be better than your standard classifiers. Again, they are harder to get, but once you go through the pain of getting them, then you would maybe expect that they are just better than the standard classifiers in all accounts. So they're definitely robust, but also you would expect that they are also have higher standard accuracy as well. Okay, so why would you think so? Well, if you know a little bit about machine learning, and in particular deep learning, you know that one very successful technique for improving the standard generalization of the classifier is to use data augmentation. So roughly what you do is essentially you not only kind of present the classifiers with your image, like image of a cat from a training set, like only that image, you actually derive some different variation of this of this cat. Maybe you rotate it a bit, maybe you kind of crop different parts of it. Essentially, like you do a bunch of transformations to this to this cat, so to make it and like kind of provide the classifier with some more diversity of the training data that you have. Okay, so you kind of try to augment this, and and this is kind of known to significantly improve test accuracy. Again, like it's just a standard thing that all the deep neural networks do actually, like when you train them, that you actually do, this is just a part of the workflow by now. No one even thinks about it because it's just happening there. So now you might think, if you know of data augmentation, you might think if you look back to adversarial training, then you kind of can view it as the data augmentation on steroids. Because in some ways, so what does adversarial training do? It just says, oh, take a training set, a training example, and then figure out what is the transformation in this training example that actually, confuses your the model the most. So in some ways, you really are thinking like, what is the most, if you were to teach someone, is you would like to show them example that is the most confusing to them. So you can kind of provide them with advice on this example because you expect that this will give them the most help in learning the concept. So again, so if you are thinking, if you are thinking that adversarial training is essentially this data augmentation on steroids, then it would be natural to expect that adversarial training improves standard accuracy as well. It definitely improves robust accuracy, but it also improves standard accuracy. Okay, so there's a question, by the way, like how do you use unlabeled data for augmentation? So I think you mean, well, you can definitely do data augmentation with unlabeled data because you don't need to know the label to do augmentation. You can do crops and rotations of anything, but I guess you are referring to, essentially, you are referring to how do you use it to augment robust training. And roughly the idea is that if you think about what robustness is, you can view it not necessarily as just a question of, oh, for every training example, kind of give me the right answer no matter how I perturb you. Actually, you can also see that what is helpful, just say, okay, whatever you do, like whatever is your answer on this training example, just make sure it's consistent as I perturb the example. So in some ways, the way you use unlabeled data, you just don't say, no, any answer is good to me on this example, as long as it's consistent as I start perturbing you. So I just care about whether I can flip your answer or not. I don't care if your whatever answer you are sticking to is correct or not, because I don't have the label anyway. But like I will just like try to penalize you if it's possible on this training point to just flip your answer, that you kind of don't stick to your guns. So that's kind of the idea behind like how you would use unlabeled data to help with robust training. Of course, you need some labeled examples to, in the end, figure out what are the right labels. But the point is that to just encourage robustness, you kind of, you get a lot of mileage by just, essentially ensuring invariance. Okay, does it make sense? Good. Okay. So here we are. So this is the question. So does a robust adversarial training improve standard accuracy? And the answer is not quite. So this is kind of an example run of like essentially I'm comparing kind of the standard accuracy of a standardly trained model, which is red, and and robustly trained model. And as you see, like kind of there are these two regimes. In the small sample regime, like when my training set is not too large, it's actually robust training does help. Like it seems to have advantages over standard training in this small data regime. But the moment we get into large data regime, kind of training robustly is actually not only not a benefit, but it actually is a penalty. Like actually you end up having worse standard accuracy than what standard training would provide you. So here's the question, why are robust models less accurate? Again, we are talking about standard accuracy, not robust accuracy here. They are still very much more robust than the standard classifiers, but now we are kind of measuring them on standard accuracy. Okay, so essentially the kind of the theorem you can show, or this is also like an observation. It's a theorem, but it's really like an observation, like meaning in terms of like what is really going on, is that there is a kind of this inherent on some distributions, at least, there can exist an inherent trade-off between the standard accuracy and robustness. So you might not be able to get best of two worlds. And kind of the intuition is you just think of the following distribution in which all coordinates are independent again, and there's a few coordinates that have strong correlation with the correct label, and then there's a lot of independent coordinates that have very weak correlation with the correct label. Okay, so now if you think of the standard training, well, the standard model, what it will do, it will just try to maximize all the information it can get about the label from all the correlations. So in particular, even though there is like a lot of coordinates that are only very weakly correlated with the label, well, there is a lot of them that are independent. So by concentration law, you know that overall, you can aggregate all of this information into actually very strong signal. However, if you think about a kind of robust classifiers, well, essentially what happens there is that you cannot really use this weakly correlated labels, because essentially if you try to do that, then the adversary can just push a little bit tiny, as we have seen in the previous example when we analyze the hard distribution. It just like can push all of them a little bit and kind of completely undermine this this distributed correlation among these weakly correlated examples, and completely make your model non-robust. So essentially, like if you want to be robust, you have to just stick to this, the strongly correlating features that essentially the adversary cannot really hurt you by perturbing. So that's fine, that makes you robust, but then you are kind of missing out on the information that you could get from these other features, and this way your standard accuracy actually suffers. Okay, so there is a kind of the there is this kind of trade-off over here, that kind of, yes, there is information available, but if your classifier wants to rely on this information, it exposes itself to being misled by the adversary. So it just essentially, if you want to be robust, it has to forego this information. And the standard classifier doesn't care; it just gets all the information it can actually get. Okay. So this is kind of the phenomena at play. Yeah, so there is this comment that it sounds like robust training works like a form of regularization for a neural network, and this is like exactly that. And we will actually talk about this in the next lecture a little bit, but this is kind of the view that outside of just robustness for the sake of robustness, you can view robust training as a form of regularization. And again, I will also talk a little bit about this just in a moment. Okay, so that's a very good point. Okay, So now we know that like robust training needs more data. We know kind of that there might be this trade-off between being robust and having good, strong accuracy. And yeah, okay, so there is someone wants just us to go a little bit again over this graph. So again, so what's on this graph is on the x-axis, we have just the size of the data set. Okay, so we have these two regimes: small sample, meaning small training set, and large training set regimes. And now what we are plotting here is, well, we take robust training and we say, okay, if I train a classifier robustly on, let's say this size of a training set, what will be the accuracy I will get, like the actual standard accuracy I will get. Okay, so again, the accuracy is just standard. There is no adversary there. I use robust training, but there's no adversary when I evaluate things. I just want to say what fraction of test examples I get right. So this is kind of what this curve tells me, and the red curve tells me the same thing for the standard training. And as you see that, like once you kind of move from this kind of small sample regime to the large sample regime, training robustly is actually kind of counter, like it's actually lowering your standard accuracy, as opposed to increasing it, or at least matching what you would get from from the benchmark of standard training. Does this make sense?
And sorry, how does this graph compare to the previous graphs where you also compared robust?
Yeah.
There was no phenomenon of crossing of those curves.
Yes, there was no. So that's a great thing. Yes. So in some ways, yes. So in some ways you can view, but that's how you can view it. So essentially, like as you see, the curve doesn't really start over here. So essentially, like it just all the action I'm talking about is happening over here in this small. So the small is really small.
Okay, so it might cross those two curves, the blue and red, might cross somewhere to the left of this, which is not measured in this plot.
Yes. Yeah, so essentially, like, so this is the funny thing, that like this test accuracy is measured with a different standard, and the training is like essentially like, yeah, so here we look at the robust accuracy, but essentially like you will look actually like actually I don't remember how we train all these 4 models here, like because this is just how we test them. It might be actually that all of them are trained in the same way. So in some ways, the kind of this might be apples and oranges comparison. Actually, I don't remember now what this plot is, but like in any case, like this regime when things are helpful is fairly small. But yeah, again, I guess it takes up to 10,000 samples. So probably what happened in that plot was that we trained the model the same. We just evaluated, with different accuracies. I would need to look back what is there.
There's another question on the chat.
Yes, so that's similar crossing across with strong regularization. Yes, in some ways, yes, and again, there are reasons for that. Like kind of there is a, like this kind of comment before that you can view, that you can think of robust training as some kind of regularization is very much on spot. Okay, and again, we will look into it in a moment. Okay. But it's a very good comment. Okay, so now we kind of provide 2 visionettes of like why learning robust classifiers might be hard. So now kind of the mystery to me that kind of was actually the biggest mystery of all of this is but like why this is such a big problem to begin with. Like why our classifiers so bad at being robust? Again, we didn't design them initially to be robust, but like why do they fail so badly? Like kind of they might not be great, that's not surprising, but like why they're like so bad in being robust. So in particular, yes, like we know kind of, how to make them more robust, and we know what robustness means, but like this does not tell us, kind of why things are the way they are. In particular, they don't tell us, why adversarial perturbations exist and are so widespread. Just the fact that they can exist doesn't mean that they should exist, but they do. Why this perturbation tend to transfer? I already told you about this, that like somehow perturbation created for one model ends up often working for different model as well. And again, this is a mystery this was a mystery to me. And why robust training works, like, again, there is some intuition why it works, but like, why does it generalize? So it's clear why by solving this min-max problem, you can fit the training set, but why this performance still tends to generalize pretty well to unseen examples that kind of, are, and kind of, you have to realize this is like high dimensional distributions. Like you really in training set, the training set doesn't cover kind of, in any, like there's no epsilon there that you can say that, every test point is like close to one of the training points. That's totally not how these networks work. So there has to be some phenomenon at play that kind of allows us to being robust on the training set to transfer to being robust on this test set. And also there is a certain different technique to make models robust. It's called randomized smoothing, and I will talk about it in a moment. And kind of the question is why this technique is successful as well. Okay, so let's talk about this question, and let's start with the first one. So yeah, so this is the question. So why are our models brittle? Okay, and we are definitely not the first one to ask this question. Like there was plenty of people asking these questions and plenty of people trying to provide an answer. And the answers differ. They say, oh, this is a high dimensional distribution, so there always will be some directions that kind of are wonky. So that's the problem. They say, oh, we are subsampling the distributions. There is like a finite sampling effect, and again, that's what we are observing. There are explanations that just says, well, you are training your models to be good in expectation. So there is just like, you should be ready and kind of accept the fact that, that they will not be good at being robust, which is, again, it's a valid argument, but that doesn't really explain why. And then there are explanations that say, oh, this is like a punishment, for using, deep learning, using, batch norm, or like any particular way we are doing machine learning right now. Okay, so there are many, many explanations. And kind of what all of them have in common is that they kind of view adversarial examples as an evidence of some aberration. Essentially, adversarial examples exist because there is something about the way we do machine learning that is wrong, that we didn't get yet fully right. Okay, and this is kind of the current view. And this was the view that we also kind of subscribe to. But like now we will try to challenge this view a little bit. Okay. Now, the point of start is just to ask, kind of a somewhat at first kind of a tautological question, or like essentially like, kind of a silly question. It's like, why are adversarial perturbations bad? Okay, well, they are bad because, what happens is that, I have this beautiful picture of a dog. Then I add to it some meaningless and small noise, and I get a new picture that is still very much a dog to me, but my model insists that that's a cat. Clearly, like this is really upsetting. This is really not kind of clearly the model got something wrong, because on the left is the dog and on the right is the dog as well, and this perturbation didn't change anything. So why why do we have a change in the decision of the model? Okay, so this is a valid reason to be upset. But the important point is to realize that this is kind of coming from our human perspective. In some ways, we know what a dog is, and to us, that's kind of what just played out. Like there was a dog, you add something to something meaningless to it, and then you supposedly get a cat, even though this is still very much a dog. Okay, but we need to understand that this is like this human perspective, right? Like the way when we are tasked with the question of distinguishing dogs from cats, essentially, well, we know how you are supposed to do it. You should look at the snout, you should look at the shape of the ears and the texture of the fur. Like that's how you recognize if this is a dog and a cat. So that's kind of how we humans do it. And kind of that's why subconsciously we also expect that this is how machine learning models do it. However, if you think about this task of like, of distinguishing cats versus dogs from a machine learning perspective, well, you realize that, well, to a neural network, image is meaningless. Like it doesn't have even a concept of an image. To it, image is just a vector of numbers. Okay. Also, like the notion of a class dog is meaningless. It doesn't have a concept of a dog. This is just a string of characters. And the only goal it has is just saying, well, there are strings of like vectors of numbers and string of characters, and I need to make sure I kind of match these two like in a way that makes my test accuracy be as large as possible. That's the only sole goal that we expect of this neural network. Okay, and that's what it strives to deliver. So in particular, if you take into the account, like this, dog versus cat kind of classification challenge, and you want to really understand how it looks like from the point of view of your machine learning models, maybe you should not be thinking about dogs versus cats, but you should be thinking about the task of classifying taps versus talks. What are taps and talks? I have no idea, but that's exactly the point. I just, have some, kind of squares of, of different colors shown to me, and there are these two classes, tap and talk. And well, maybe I will notice that by looking at enough of these that, like, if this rectangle is present and this is a class tap, and if this rectangle is present, this is a class talk. But honestly, ultimately, that's kind of all understanding of the classification task that I see. And in some ways, that's how probably the task of cat versus dogs looks like to our model. Like, there is kind of just like a purely meaningless thing, just like tries to figure out any pattern that allows it to make sense out of this mess. Okay, and now from this ML perspective, so like the adversarial examples we tend to think is this kind of dog becoming a cat, but from the point of view of kind of machine learning model, what happens is that there was an example of a class tap, then there was some meaningless perturbation, and we have an example of a class talk. If I ask you like kind of this adversarial example on the bottom, it doesn't really seem upsetting, does it? Like, it kind of says, whatever, I had some, some rectangles on the left, I have some other rectangles on the right, and I just changed some rectangles and it changed the class. Like, it doesn't seem upsetting, right? In particular, like, can you even say that this is a meaningless perturbation? Like, what meaningless means in this context when everything is meaningless to us? Okay, so this is kind of what, like this kind of perspective kind of motivates us to ask, okay, so, we tend, when we see these adversarial perturbations, we view them as completely meaningless. But are they actually meaningless? Like, they're meaningless to us, but are they actually meaningless to the machine learning model? Okay, so here is a simple experiment to test that. Okay, so what we do is just following. So imagine I have a training set of cats versus dogs, like a standard training set I get. But now I modify it in some way. So what I do is I take every image of a dog in my training set, and I find an adversarial example that makes some pre-trained model believe that this is a cat. Okay, so I just kind of add this adversarial perturbation, and then I flip the label of this, like, so essentially like this adversarial cat is now labeled as a cat. Okay, so even though it still looks like a dog to me, I label it as a cat. And I do the same to every cat. So every cat in my training set, I find a adversarial example that makes my model believe that this is a dog. And then I flip the label. Okay, so that's how I create a new training set. Now I have a new training set. Well, if I have a new training set, I can test, I can train a completely new model just on this training set, sorry. Well, I train my classifier on this training set, and now I want to test it. But I actually want to test it on the original test set, like the unmodified test set. Okay, and I want to see what the performance will be. Okay, so what just happened here, right? Like, what we expect will happen here. So like we have this training set in which, to us, every dog in this test set is labeled as a cat, and every cat in this test set is labeled as a dog. So to us, this data set looks totally mislabeled. So if you didn't speak English and you didn't know what dog and cat means, and you just got this training set, you would quickly conclude that, in English, cat is a dog and dog is a cat. Okay, so if you would test the original test, you essentially would expect that you will fail miserably. Essentially, you will get 0 accuracy because you always will give the wrong answer. Okay, so this is what will happen if I give it to a human. Now, what happens if I train a model on this and I make it go through this test? Well, the surprise is that the model actually does pretty well on this original test set. So it's still, like, for a CFAR version of this challenge, you get like 78% accuracy. Again, human would get 0, but the model gets 78%. What's going on here? Like, how can this happen? Like, could our intuition be so wrong? Well, we are trying to think. Well, first thing that we checked is we checked, okay, is the maybe the code wrong? It wasn't. it really was what it was. So then, what we realized is, okay, so we looked back at all our thinking in kind of when we went through this, like, this Gedanken experiment, like this thought experiment, kind of like what could go wrong there. And we realized that there's only one piece, one step there in which, things could have gone wrong. And essentially, like, the only thing that we kind of wanted to, like, we instinctively assumed is we assumed that these adversarial perturbations that we added to create this new training set, that they are kind of meaningless. They're just some kind of aberrations. But clearly, they need to convey some information. So in particular, what we kind of realize is that kind of when we think about the features that one can use for solving classification tasks. So, well, the original picture was that there are kind of, it's essentially like, you were thinking that there are kind of only one type of features, like that there are kind of also like robust features, like features that, there's just features that are kind of correlated with the label. Even, even when kind of adversary tries to change the picture a little bit, they are still there. So think of things like, we as humans use like ears or snout, like it does not get affected by just imperceptible changes to the image. Okay, and you kind of tend that everything we use for classification falls into this umbrella of what we call robust features. But as much as we think that this is the way we do the kind of classification, does not mean that that's the only way to do classification. So essentially what we essentially have shown that there exists this non-robust features. So features that actually correlate with label very well on average, but they can be flipped by this tiny, even by these tiny perturbations. Okay, and kind of now what happens is that, like, well, the only thing that the models are interested in, they're not interested in mimicking us. They're just interested in the maximizing the test accuracy. So to them, any features that correlate with the label are a fair game. And it turns out that these non-robust features are often great at actually correlating, correlating with the label. So essentially, our model tends to pick on them quite a bit. They rely on these features quite a bit, and that's what makes them vulnerable to this adversarial perturbations. Okay, so in particular, if you look at our experiment, from this perspective, what we realized is that kind of essentially at the beginning, we had this like robust features, and they were correlated with being like, with dog being a dog, and we have this non-robust features which correlate with, with also dog being a dog. But in our new training set, well, essentially what happens is that, now the robust features are misleading because, the robust features, they didn't get affected and they are still saying this is dog, even though now the label is saying a cat. But the non-robust features, well, they flipped as well. So I flipped the label, but I also flipped the non-robust features by applying the perturbations. So the correlation is there. And since our models like to depend on that non-robust features anyway, kind of this provides enough of correct information that they actually can get very much non-trivial accuracy on the original task. Okay, so kind of okay, so essentially, like, yes, so that's what happens. So kind of essentially, like, this is how how this performance of the original test set came about, because we still could leverage this correlation between non-robust features and the correct label, because that's what the models like to use anyway. Okay, so kind of the emerging kind of realization here is that essentially essentially that there's kind of this perspective of, and something that again in the hindsight is obvious, but kind of we didn't think of this, is just this difference between the human and ML model priors. So essentially, like, when we again think about solving this cat versus dogs task, we as humans know how you are supposed to solve it, but it doesn't mean that this is the only way to solve it. It turns out that there are other ways to solve this dog versus versus cat classification challenge, and a priori there are equally valid ways to solve it because they lead to to good accuracy. So you should not expect a priori that your model will use the kind of the human preferred one just because you like it. It will use whatever gets it the maximum accuracy, and as it turns out, it's often not the way, not what you would think is the right thing. So in some ways, it shows that adversarial examples are a human phenomenon. So there is nothing, there is nothing wrong with the fact, inherently wrong, that the models tend to have adversarial examples. Because again, what really happens is that, these perturbations, they really change the features that the model judges salient for predicting this is a dog and a cat. So in some ways, to an ML model, this perturbation flipped the image from cat to dog in a substantial way. It's not just some kind of malfunction. This is actually like semantics of the image change. The fact that we ignore the features that the model looks at like makes it confusing to us because something invisible happened to us, but to a model, it's plain that like, cat was changed in the dog. And the only reason why we don't like it is because we as humans have a different perspective, what makes cat a cat and what makes dog a dog. Okay, and actually like just addressing the actual question that just appeared in the channel, it has very interesting, implications for interpretability. So, one of the important questions and kind of issues when using, machine learning is this question of interpretability. So, these neural networks, they are just big black boxes. They spew out answers and the answers are surprisingly often correct, but we often have no idea why they do whatever they do. And you would like to be able to actually scrutinize this decision, understand why, especially when it malfunctions, why did this model made the decision that it made? And kind of, there is a whole kind of industry of developing models for developing methods for like imbuing models with interpretability. It's like many of them are post hoc, meaning you train the model and then you give it to me and I will try to infer kind of whether what makes this model tick. And what this kind of realization we talk about tells you is that, well, essentially if your model is using in its decisions features that just make no sense to you, and you can't really make, and you can't really make much sense of them in the first place, then the interpretability model will not help you. Interpretability method will not help you at this point, because either it will tell you what makes the model tick, but then you will have no idea, like you will not be able to comprehend it, or it will give you something nice and something you can very much comprehend, but then clearly it will suppress some important aspects of how the model makes decisions. So essentially, like if you want to have interpretable models, you need this additional restriction priors on what the features model should use in the first place. So that's kind of the regularization part. That like, kind of, if you want your model to be particularly robust, you have to kind of tell it, oh, hey, the things that that you use in your decision should be things that that essentially like are more close to what I use in the in prediction, because this way I know that like the things that do not change my decision do not change your decision either. Okay, so there is kind of this alignment. So there's a question, how good are the non-robust features in the context of generalization? So that's a good question. Like again, the experiment already suggests that they are pretty good, because again you have the situation where the non-robust features say one thing, they give you the correct answer, and robust features tell you the opposite, and your accuracy is 78%. So clearly, like in some ways, they definitely are more useful than the standard features for the model to generalize. And actually, like we talked last time that on the ImageNet, the neural networks tend to get a superhuman performance. They actually outperform the accuracy of a human, or seem to. Again, we never measured in a scientific manner. It was just a single experiment. Then kind of the conjecture would be that maybe it's because the models can leverage these non-robust features that we as humans do not really pay attention to, and that gives them additional edge. Okay, so again, it's not to say that the models do not use robust features as well. It just seems that they rely on them, well, to a significantly less degree than we. But it's a good question, like how far can you get? And we can kind of measure it. But like the point is that they are really, really good. It doesn't mean that you should discard robust features, but they are actually really, really good. Okay, a bunch of questions. So does model architecture impact choosing between robust and non-robust features? Of course it does. In some ways, humans, you can view them as an architecture that kind of relies on robust features. Of course, like it's a bit of a circular argument, because the way we define what robust means is anything that our system kind of would be robust to. But like yeah, there's clearly there is an architecture here that makes things more robust. But indeed, also beyond that, like like I very much believe that there is a way of designing an architecture for neural network that makes it much more robust. In some ways, you can think of adversarial training essentially, like you can use adversarial training as a viewing of as a like software patch on the architecture problem. Like kind of, instead of solving it in hardware in your architecture, you kind of do the training to kind of fix the shortcomings of the architectures we are using from the point of view of robustness. So I very much believe that like there is some architectures that will be much more robust. How generative networks overcome this ML? This ML emphasize on non-robust features. Well, again, generative model, I don't want to go there, to be honest, because that's a separate discussion. But like the point is that the generative models have a very different goal. Kind of, they are heavily regularized to generate things that look like human. And actually, like if you try to implement a GAN from get-go, just like from the basic, like the saddle point formation, but by the way, it's very similar and for good reasons with, well, to the adversarial training, then you don't get anything interesting. And again, actually, we'll talk about this a little bit in the next lecture. So maybe ask this question there. But like the point is that I wouldn't say that generative networks overcome it. They essentially sidestep this issue. And I can tell you more. And actually, there are some experiments that kind of relate to that in the next lecture. Human intuition uses non-robust features. I don't know. Like this is, by the way, like I started because of this point of view. Like this is actually connects a lot to neuroscience, because it kind of starts to kind of make you believe like what makes the human vision system different to neural network system, to neural networks like the artificial neural networks. And actually, that's a whole topic of study in neuroscience. Like people work on this for decades by now, and they have some interesting intuition, but they were like actually found these things original and interesting. Actually, there are some papers now that based on this work in neuroscience that kind of try to show that this is another way, robust training is another way to kind of narrow the gap between the artificial neural networks and how the human human visual system works. Okay, so I'm essentially out of time. I did not get to the to everything that I wanted to do, but that's fine. We'll just do it next time. So essentially, like I hope that the takeaway from the class today is that kind of there is this kind of really this like human versus ML misalignment that is kind of a big driving factor of non-robustness of the models. Again, and as you will see in the next lecture, it just actually like explains a lot of phenomena that we see can be explained exactly, in this framework of like, just this mismatch of what models pay attention to and what humans pay attention to. And kind of once you correct for that, like the mysteries stop being mysteries. And yeah, so essentially like, the plan for the next lecture will be to kind of finish this, like kind of just show you like how the phenomena we observed can be explained in this framework very easily. And then we will talk a little bit about kind of properties of like, essentially like, it's clear by now that you can think of robustness as a regularizer. So not only just robustness for the sake of robustness, but essentially as a regularizer. And essentially, we will see what are, how useful robustness as a regularizing technique actually is. Okay, so that's all I have for today, for you today, and yeah, and see you tomorrow.
Thank you very much. I don't know if
yes, so if there are some questions, yeah, I'm happy again. We see each other tomorrow, so you can also think of your questions and and ask them tomorrow. But by the way, you ask very good questions. Some of them are very foreshadowing what happens next, which is great. That's what you want to see. But like, yeah, I very much enjoy the question that you ask. So keep them coming. Okay.
Okay.
See you tomorrow. And today there are exercises, but like, yeah, but I will see you tomorrow.
Yeah, that's in half an hour. Bye.
Yes. Thank you.